All right, let's get started. Good morning, everyone. I'm Tyler Martin with Long. Thanks for joining another coffee break. We've got Eric Kruger with KMC Controls to talk about our new airflow measurement system that we have adopted as their standard. Eric?
Morning, guys. Like Tyler said, my name is Eric Kruger. I'm with KMC. I work out of the factory in Indiana. And today, we're going to give you a quick run through of our new KMC Conquest airflow measurement system. So I think airflow measurement is something that is certainly been around a while. I think in talking with reps and balancers and things like that, there's a lot of problems with airflow measurement, how it typically gets installed, and we'll run through a little bit about what we're doing to provide a better solution for those applications. So to start off, I mean, there's several reasons why we would want to measure outside airflow. Typically outdoor air is the most expensive thing we're going to bring into a building because we got to heat or cool it. It makes a big impact on occupant health, comfort, and overall mechanical system performance. And it's named in many of the ASHRAE standards that we all have to live by. In the COVID world, it's been interesting because everybody's response is, I want to bring in as much outdoor air and ventilation as possible. Many times that's measured. The hard part there is the measurement technology that's out there doesn't always provide the best or accurate data by the nature of where we all have to install it. So, while we might think we're bringing in enough outside air or, not bringing in too much, many times that data just isn't reliable. So what we've done is we've come up with a new product, our airflow measurement system. We characterize the airflow through an entire piece of equipment through something we call a learn mode sequence. And then after we generate that data and store that data, we can provide reliable and accurate outdoor supply and return airflow for monitoring or direct control of those different airflows. We can do all this by referencing the methods described in the ASHRAE standards, the same standards that airflow balancers would use to measure and monitor those airflows. And again, that could be just for measurement, or I could use that for integrated unit control as needed. One of the biggest issues out there with other types of measurement, whether it's thermal dispersion or a hot wire anemometer or an orifice plate, is they're generally not fit for all types of equipment. You're not going to install it on a rooftop or a unit ventilator or a fan coil with a fresh air inlet because it's not physically possible with enough straight duct runs or other, sheet metal geometries. There's also airflow components that affect measurement. So, turbulent air versus laminar flow, low air velocities versus, something that's reasonable enough to make the hot wire accurate, et cetera, et cetera. All of those facets add up to unrepeatable measurements and inaccurate data. So our system, to give you a good high-level overview, is we apply a supply air measurement in the proper location. That could be in a fan inlet. It's a high velocity, highly repeatable signal, or it could be downstream in the ductwork in a proper location. We also install an inclinometer on the mixed air damper assembly, so we can capture the movement of the modulating parts of the mechanical system. And then we also take temperature readings from OA, return, and mixed air. With all of this data, and if I put it through our patented calculations that are based on ASHRAE 111, which is the balancing standard, I can accurately measure the airflow coming from outside return through that supply air fan. So how we do that. I mentioned the learn mode already. Again, that ASHRAE 111 standard has a mixed air equation that everyone needs to use if you don't have an ideal airflow pattern to take a velocity measurement. So again, that's the exact standard that the balancers that we all have to our job sites are using. What we do is we position the mixed air assembly at several different locations. So 0%, 5%, 10%, etc. And at every location, we're allowing that airflow to stabilize, the temperature measurements to stabilize, and then we go through a series of loggings or logged readings that are sampled and averaged. So we've essentially automated the balancer doing his duct traverse to build that table. After the table is created, depending on your equipment, it can take between an hour and a half. Once we've done that learn mode, the temperature measurements are there for diagnostics and faults only. And all of the airflow measurement can be based off the supply air reading and the inclinometer with the table characterization. The diagnostics that are included would be all the temperature sensor faults. We can tell if the mixed air assembly or dampers is not moving, if the airflows that we're getting don't match the ASHRAE 111 standard and something's mechanically changing your system or filters are plugged up. All of that data is resident in the Conquest airflow measurement system. So to get to the meat of it, and I think this makes a pretty clear case. We've done several sites over last year. This is a product that we're currently selling. DPS has one installed. We'll look at a few pictures of the unit that we installed out in Denver last summer. But before we do that, there's a few performance charts that kind of illustrate heads up a KMC Conquest AFMS data versus the other technologies that are out there. So in this chart, the blue line is our airflow data. This was a air handler out east in Connecticut, and it happened to have a professionally installed third-party balanced 2 thermal dispersion systems. One was an Ebtron, one was a Ruskin. So the red line is the Ebtron, the green line is the Ruskin, the gold line is the ASHRAE 111 number. So if a balancer was there taking a traverse, that's the number he would have generated. Here we start at the damper is about 65% open. I would say that everybody's number is pretty flat. We're right on the standard. Ebtron and Ruskin are similar. They're a little high. I would say we could probably fix that with a calibration or a magnification factor change. Same thing if we're modulating that damper further open. They're overreading, but it's a standard offset. The only thing I really see here is that their numbers are fairly jagged, which again can be common in velocity measurements that probably are fairly close to the damper assembly. This becomes more interesting as we modulate that damper closed in the middle and we get to very low velocities of airflow. The red line, again, that was the Ebtron, is still reading about 5,000 to 6,000 CFM, even though the damper is only 5% open. So that's a problem. The Ruskin, the other thermal dispersion sensor, the velocity is so low that it can't read anything. So now, even though I am bringing in some airflow, I'm not capturing that data. You can see here the gold line, as those thermistors saturate and become accurate at the new airflow temperatures, the blue line, the KMC line, is right along the standard as it should be. This was the same system on another day where it happened to be raining. This is a big built-up air handler with a louver through the wall in the attic. It was pulling in some of that rain into the louver, and the Ruskin and Ebtrons were getting some moisture on them. I think we've all experienced probably where I'm pulling in moisture onto that hot wire. It's going to cool off the elements faster, meaning it's going to read higher and overestimate what airflow is being brought in. So these numbers become very erratic. If we're using the other technology, there's measurement variances of 6,000 to 7,000 CFM between samples, which doesn't create for good or accurate control of that OA. for that mechanical system. The last chart that I'll show is a unit that we did here at our office. The long story short is that by the nature of our measurement and our characterization that we've patented on this thing, the return and outside air will always add up to the supply total. We don't have situations where I have independent measurements that are reporting to my end user that I have more OA than supply. So we'll look at a couple pilot studies. This was one of our rooftops. Shows you how small of a unit you can install these components into and get an accurate airflow. It's about a half a man day total for most of these sites. And we've all looked inside of a unit. On the right, you see we're picking up our fan inlet measurements in a good high velocity location. Any track or any modulating piece of that mixed air assembly is something that we can grab for our characterization data. So here, even on that return air flap, that's what we're using to know what that mixed air assembly is in. Looking at an even smaller unit, we did a job that was unit ventilators in Upper Michigan. So this, instead of spending COVID money on ionization, they chose to go ventilation and get their AFMSs installed. Here again, this is about a 2-hour project for a couple guys, and we used a coil face velocity. So depending on the geometry of the equipment, install the sensors at the best location for you. You don't have to use a fan, you don't have to use a coil velocity, you don't have to use a duct run. We can use any of those measurements, and very highly flexible options for install. This is highlighting the unit that we did out in Denver. This was a Daikin rooftop, powered exhaust. In this one, it was easier to remote mount the supply air down underneath the duct. There was already a transmitter down there. And again, this is about a half a day install for a couple guys. And at the end of that half day, we had good supply return and OA data inside Commander being reported to DPS. The other thing that I'll highlight on this side is off to the right, we have a card just to show some of the basic diagnostics. So my dampers faults are off, my outdoor air sequence is operating normal. I've got some delta T between return and supply. So again, very easy diagnostics that are already pre-programmed into the unit. And then the last case study I'll run through quick is one we did in Chicago. This is a whole building air handler. Kind of an interesting setup right down the street from Wrigley Field. They had multiple Ebtrons already installed. We found out through installing our system that Ebtron was reporting 52,000 CFM of outdoor air on 49,000 CFM of supply. How that's possible, I'm not sure. After we got done in our 5 man hours it took us to do it, we measured that they were under ventilating their building by 1/3 just because they weren't accommodating or accounting for the leakage in those return air dampers that you'd see on the right and left of the picture. This airflow station is also integrated pneumatically. There are 5 receiver controllers still controlling this 8-foot diameter paddle wheel fan. So kind of a unique install. Airflow station works the same way, same pieces and parts that get applied to the unit ventilator accommodated this 55,000 CFM air handler. So more Commander cards and diagnostics. And after that, it's time for a giveaway.
Awesome, thanks, Eric.
Sure.
Anybody has any questions, see your Long salesperson for more info. Thanks, everybody. Just a reminder, next Friday is the Rockies home opener. See your salesperson at Long for details on our party. Have a great day.